Linear algebra studies vectors. So in this video, I will give you our definition of what a vector is and introduce you to three fundamental examples of different kinds of vectors. In subsequent videos, we'll discuss each one of these kinds of vectors in great detail, and these three fundamental examples will accompany us throughout our linear algebra journey. So let's now talk about what a vector is. As I mentioned before, linear algebra studies different kinds of objects that can be added together and multiplied by a number to produce another object of the same kind. So that's exactly what a vector is. Vectors are the kinds of objects that can be added together and multiplied by numbers to produce another object of the same kind. So any object that satisfies these two simple properties can be considered a vector, and linear algebra has something very interesting to say about it. You're already familiar with one such object, and that's audio signals. But audio signals are rather complicated, and we'll definitely talk about audio signals in greater detail, but we'll save it until the later part of the course. So I now would like to introduce you to much simpler and more fundamental kinds of vectors. And the main takeaway is just how different these examples are. Let's start with geometric vectors. What are geometric vectors? Well, they're a very straightforward thing. A geometric vector is simply a directed segment. That's all it is, a segment with a chosen direction. Geometric vectors can be drawn in the two-dimensional plane or along a one-dimensional line, or imagined in the three-dimensional space. In either case, geometric vectors are very simple objects, and they're probably the least abstract objects you've encountered in mathematics in a very long time. Why? Well, we're simply talking about drawings, and that makes them simple and, in a certain sense, a little bit complicated, because I know that a lot of students coming out of high school really didn't like geometry. Well, this is your perfect opportunity to fall in love with geometry, or at least some of the most basic elements of geometry. And that's all we'll really need, just the very fundamental concepts from geometry, such as straight lines, planes, right angles, a little bit of triangles. Now, it's important to realize that much of inspiration and intuition for linear algebra comes from the world of geometric vectors. You will very frequently be able to answer a complicated question in linear algebra and beyond simply by imagining a very simple geometric picture involving geometric vectors. That's how important this kind of vectors is. And of course, you're probably already realizing that much of the terminology of linear algebra comes precisely from geometric vectors, including the word vector itself. This is the original meaning of the word vector, and it has since been generalized to its linear algebra meaning of any kind of object that can be added together and multiplied by a number. But this was the original meaning. Other terms that come from geometric vectors is space. We'll talk about linear spaces, clearly a geometric term, including subspace, plane. Then we'll use terms like transformation, distance, angle, dot product. All of these fundamental ideas, pillars of linear algebra, come from the world of geometric vectors. That's the importance of this class of vectors. So it's very important to overcome whatever dislike you have for geometry and fall in love with these very elegant, beautiful, and insightful vectors. It will really be of tremendous benefit to you, whether you're a mathematician, a physicist, a chemist, or an engineer, an economist, or anything else. The world of science started here, and it's still very important because that's where imagination is at its most vivid. Now, of course, I still owe you a definition of what it means to add two directed segments or multiply a directed segment by a number. And I think it's pretty clear what it means to multiply the directed segment by a number. It means to keep its direction and increase its length by this number. And I think a lot of you know what it means to add two vectors, but in this course we'll start from the very beginning and give you the definition for the sum and explain why it is a very intuitive definition. So that will happen in one of the subsequent videos. So for now, I would like to move on to polynomials, but keep in mind that this will be one of the most important examples of vectors. Now let's talk about polynomials. So I actually don't have much to say about polynomials because you already know perfectly well what polynomials are. They're just these kinds of expressions. Except now I would like for you to think of them as vectors. Indeed, can two polynomials be added together and is the result another polynomial? Absolutely. And can a polynomial be multiplied by a number and is the result another polynomial? Absolutely. So polynomials are vectors. Great. And we don't even have to limit our attention to polynomials. We can throw in sines and cosines and exponential functions and rational functions and all other kinds of functions and talk about functions in general as vectors. Because once again, can you add two functions and is the result another function? Of course it is. And can you multiply a function by a number and is the result another function? Of course, yes. So functions, just as polynomials, are vectors. And we will call polynomials a subspace, a vector subspace of the space of functions. And you're seeing how the terminology of linear algebra comes from the space of geometric vectors. Now, two notes. Number one, why is this space so important? Well, this space of vectors is particularly important in applied mathematics and physics because mathematicians and physicists have a perhaps healthy obsession with exact mathematical expressions. They like to capture phenomena with simple mathematical expressions. That's their aesthetic, and I subscribe to it. And that's why this space, this vector space, is particularly important in, once again, applied mathematics and physics. Point number two, I would like for you to pay attention to just how different these vectors are from geometric vectors. They really couldn't be any more different. What are geometric vectors? Well, geometric vectors are drawings, which is a human activity that goes back, I don't know, probably to Neanderthals. And what are polynomials? They're abstract symbols on a blackboard or a piece of paper, something that goes back 300, perhaps 400 years, and in their current form, maybe even not that far back. So these two kinds of vectors really couldn't be any more different. And we'll repeat it over and over again, that linear algebra focuses on the similarities between objects. And the similarity between these two types of objects is that they can be both added together to produce another object of the same kind and multiplied by numbers to produce another object of the same kind. And that's probably it. There's probably nothing else that polynomials and geometric vectors have in common. Yet, linear algebra is applicable equally well to both of these spaces. So linear algebra, as we'll put it later, celebrates diversity while taking advantage of the commonality. And as you ponder the dramatic difference between these two kinds of vectors, let's turn our attention to Rn. What is Rn? Well, from a certain point of view, it's the simplest kind of vector, a simple kind of vector to think about. And from a different point of view, it's the most abstract kind of vector you can imagine. Rn is sets of numbers. Here I have examples of triplets of numbers. So what we're looking at here is elements of R3. So it's this funny R with a double bar, and the power, you can call it, the exponent, indicates how many numbers there are in a set. And we write these numbers in square brackets as little columns. So this is n-tuple of numbers. This is a special case of Rn, R3, triplets of numbers. So very simple, yes, but only if you have the abstract part of your brain adequately developed, which all of you have, because this is really as abstract as it gets. We're talking about triplets of numbers. When in everyday life have you ever seen a triplet of numbers? It's something that quote unquote doesn't exist. You can argue that all of these are figments of our imagination, but in this case I would say it's the least natural kind of object, but that is only until you get used to it. Once you get used to triplets of numbers or sets of n numbers, you can call them n-tuples, you begin to think of it as the most natural thing in the world until you give it a second thought. So I'll go back and forth, but I do submit that this is a very simple kind of vectors, and it's very straightforward to define what it means to add two vectors. They have to be of the same size, from the same space, and then you just add them entry by entry. So adding these two vectors will be 8, 7/2, and 12. And it's just as easy to define what it means to multiply a vector by a number. So here I'm multiplying it by -1/2. And the result will be -1/2, -1, -3/2. So they are indeed vectors. And they're very important kinds of vectors for several reasons that will become apparent throughout the course. Number one, all of the robust algorithms of linear algebra are stated in Rn. We'll study Gaussian elimination. And then the eigenvalue algorithm sounds like a funny word, very important concept. And many, many more will be formulated and explored in Rn in terms of sets of numbers. Number two, computers come in handy. And computers are all about manipulating numbers. And so a computer is particularly helpful if you can restate your problem in terms of sets of numbers. So that's advantage or importance number two of this space. It is perfectly suited for analysis by the computer. And then finally, later on in the course, we will show that there is a way to draw a one-to-one correspondence, really an equivalence, between any kind of vector and Rn. So by studying Rn, we're actually studying all of the other vector spaces. And that's the importance number three of this space. So yes, it's the most abstract, but in some very real sense, it's the most useful space that one can study. In fact, most linear algebra courses focus almost exclusively on this space. And that's a perfectly legitimate way to approach linear algebra. It's just that I happen to like a slightly different approach, and I think that you will like it too. So this is probably a pretty good point to wrap up this video, in which we gave our fundamental definition of the vector and considered three of the most important examples of different kinds of vectors. We will next discuss each one of these kinds of vectors in some detail. And the main takeaway is just how different these examples are. Yes!